Okay. Today we are going to focus on the echocardiogram, and we are going to check on the basic principles of echocardiography so that you can be able to understand to do echo as one of the major diagnoses in the basic diagnosis in cardiovascular diseases. So before you study much about echocardiogram, you have to understand some basic rules and some basic understanding, and that is our topic today for the introduction of echocardiogram. For the introduction of echocardiogram, that is our today's topic. So in this course of today's about echocardiogram, you have at the end of the day, be able to understand the introduction to ultrasound, transducers, display and scanning models, basic principles of Doppler, echo and ECG instrumentation, ultrasound imaging, observation and artifact and pitfalls of imaging. So in the introduction of ultrasound is that ultrasound is an imaging technology that uses high frequency sound waves to characterize the tissues. So the terminology mostly commonly used, you can either use ultrasonography or ultrasound. So the ultrasound of the heart tends to be called echocardiogram. Echo from the word sound, cardiom from the word heart, graphic is to graphically represent the information in it. So sometimes people call it just echo. So originally it was developed during the First World War to be able to track submarine as sonar technology, and first used in medical in 1950s with a very high application in fetal biometry. So that means that in the fetal biometry, that is when we started using in human being. So let us see one of the basic. You have to understand the sounds, how it travels, how it is detected in sounds, in ultrasound, so that you can be able to understand the moment you induce a sound to the heart muscles, what are you going to receive back again. So the sound is a wavelength that is created by vibrating object and propagated through a medium from one location to another via a particular interactions. So you can see the sound wave, which is going, the wavelength is from one, the wavelength is the from one uptuned to the other, that is the wavelength. So you can see the direction of the sound and compression of waves. Those are waves which are compressed. So the amplitude is the height of the sound wave. It is the maximum increase or decrease in sound pressure. Amplitude has no relationship to a sound wavelength or frequency. So you see it is the highest peak. That is the peak. The wavelength is from one peak to the other, and the amplitude is that is the longitudinal length of the sound. So the backward and forward motion of particles in the direction of the wave creates a region of high pressure with the medium. This one results to a compression, and also region of low pressure where the particles are spread apart, which is called rarefaction. So the wavelength of a sound is the distance between successful high pressure passes or two successful low pressure pulses. So the frequency of a wavelength refers to how often the particles of a medium vibrate when a wave passes through it. And in human can hear sound, a human being can hear a frequency of 20,000 cycles per second. That is 20 to 20,000 hertz. So the frequency is measured in hertz, and if it is very high, it's called kilohertz. So so a human can hear sound with a frequency of 20 to 200 cycles per second, that is 20 to 200 kilohertz, hertz, and the frequencies of ultrasound required for diagnostic medical imaging are in the range of 1 to 20. So that means this one in human being, we just require very small. These frequencies can be obtained by using a piezoelectric materials, particularly the crystals, which are in the transducer. So can you see this is an example of a transducer? You can see the electrical supply. You can see the piezoelectric crystals, which are made of ringed. So the orientation marker, you can see where the lightings. That is more right, which point tell you to where to point. You can see the ultrasound being omitted and then the matching layer. So the piezoelectric effect also works in a reverse. So if the ultrasound energy makes a contact with the receiving crystals, it will cause the crystal to vibrate in and out, and this will produce an alternating electrical field. So the piezoelectric effect occurs in a number of natural crystals, including quartz, but the most common used substance is synthetic ceramic, which is made of zinconate 13, which is the most commonly used. So the transmitting and receiving crystals are built into the same handheld unit known as ultrasound transducer or a probe. The transducer emits ultrasound in a rapid pass and also acts as a receiver most of the time. So equation for the calculation of the distance of tissue from a transducer is equal. Distance is equal to time times speed of the sound. So speed of the sound through various medium is like propagation. You can see that in air, it is 330, in water is 1497, in fat is 1440, in blood is 1570, and in metal 300 to 600, and the soft tissue is 1540. And our interest is the soft tissues and in blood. So how does the ultrasound works? So the ultrasound is works in the interaction between the tissues and the sounds. So ultrasound with which enters tissues can be transmitted, attenuated, or reflected. So ultrasound need to be transmitted far enough into the tissues in order for the image to be produced and must reflect back to the receiving probe. So attenuation is a probe which needs to be addressed by the machine. So attenuation, that is where does it happen? If particles in a tissue are small enough, they will move as a single entity and transmit sound in an orderly manner. Coherent vibration is equal to sound. If a range of molecules are present, a coherent vibration occurs, which is it. So loss of coherence is most important caused by loss of ultrasound energy. To ensure a uniform picture so deeper areas are not darker, ultrasound uses time gain comparison. Now, attenuation and deep depth penetration. Adaptation is proportional to ultrasound frequency, that is, high frequency probes have smaller depth penetration. So high frequency is equal to shorter wavelength, which is equal to high resolution. So penetration through a medium, that is poor generation, is greater attenuation, and the near structure is visualized in a greater deal. Far distances structures poor images, and low frequency is equal to longer wavelength, which is equal to resolution. So good penetration through a medium, but less details seen. So good for imaging and deep and distance structures. So that is an example of an ultrasound. It's an example of an ultrasound machine. So you can call that is the echocardiogram, echo using the cardiac probe, using the cardiac probe. So the cardiac probe transducer is paced array or cardiac probe, low frequency of 2 to 8 megahertz, and high penetration, good for moving structures because the heart is always moving. So there are various types of transducers or probes. There's convex, linear, paced, microconvex, endocavity, linear, biplate, T-type, and intralectal and linear types types of ultrasound probes. So paced array is the one which is used in cardiovascular. So there are various modules for scanning. There is a A module, which is amplitude module. Each layer produces a reflection source up as peak on the trees. The larger the echo, the higher the peak. The higher the echo, the higher the peak. So the transmitter receiving echoes. Okay. So V mode is a bright mode. How brighter there is. Each reflection echo is registered as a brighter spot. The larger the amplitude of the reflected echoes, the brighter the spot. So you can see if in this case now, if the amplitude is high, then the ultrasound will be brighter. But if the amplitude will low, that means it is dark. So in this case, larger masses or denser masses will have a brighter. For example, you see the reason why in interceptor species you see it's becoming brighter. So multiple images line composed of various praxis of the varying brightness and created on various continuity, forming a real-time representation of cardiac structure. Among the many ultrasound controls they are usually a button marked with B, which is called B mode. And if you it's called B mode, or what you can consider the normal imaging mode. So you can see like this one, the brighter is the denser parts tissues. These are the tissues which are denser. So we have the mode, the M mode is the motion mode. That means the moving echoes is used to assess the distance between the tissue plates as they move. The most common application of this is in the echocardiography for the dynamic assessment of chambers and valves throughout the cardiac cycle. It displays the echo data for a single image line over time. So this is an example of an ultrasound. You can see this one is an image line sample. You can see that one is measuring the distance of the size of a valve. Okay, B mode, and then the B mode is measuring the intraventricular, the ventricular, left ventricular, and then it is measuring the movement there so that it can check the diastolic and the systolic in it. So there are various descriptive terminology like anechoic is a tissue which does not produce any echo, and hyperoic is a tissue that produces a strong reflection back to the transducer, and hypoic is a tissue that produces weak echoes and termed hypoic tissues. So this is the ultrasound knobs. Those are the knobs which you are supposed to familiarize yourself with. The more you practice and the more you use them, the more you understand them. Okay, so the novorology terminology is that there is a focus, much like a lens, a focus, and that is the focus part of the ultrasound beam, which gives the best resolution for structure of interest. Ideal focus should be set at the level of the point of interest. So focus is much more or like the cursor. So gain or time gainer compensation is TG, gain brightness or compensation for attenuating of the ultrasound waves that occur due to tissue interactions, gain amplifying only returning echoes, increase or decrease from all. This is like in music, the one increases the sound quality. This one is where you like the one in the ultrasound. So too bright gain and dark image, too much gain very bright image. So the depth refers to how deep the tissue, the ultrasound waves penetrate into the body tissue during the examination. That is the depth. So the Doppler effect was discovered by somebody who was called Christian Andreas Doppler in 1803 to 1853 and is commonly used as ultrasound imaging to examine the movement of liquids such as blood in the arteries and veins. Doppler effect is a phenomena that describes the change in the frequency or wavelength of a wave related. So the frequency of alteration that occur when ultrasound interacts with the moving object to qualify for the direction and velocity of a moving object. So there is current Doppler, there is power Doppler, there is spectral Doppler and past wave Doppler and a continuous wave Doppler. So these are various points of, we call them echo windows. Echo windows, you have the suprasternal. Suprasternal is just mean there above there. Then you have the left sternal, parasternal, you have the apical and the subcostal. Subcostal is used for measuring the inferior vena cava movements. Apical is the best one, which can check you either can it take you the plaques, it can also take you the salt axis, and the other one is used for checking the supra sternal is for checking the intraventricular septum. Okay, ventricular septum. So those are various types of windows. So those are the various windows. So when you look at the left parasternal long axis, that is the type, that is where you'll be able to see the apex of the heart, the papillary muscles, which owns the valves. The left ventricle, the interior was the left ventricle, mitral valves, the left atrium, and the aortic valve and aortic arc. Left ventricle outlet, outflow, you'll be able to see it. That one, and that one is represented in an ultrasound like the one up there. You can see the septum, the left ventricular outlet. You can see right ventricular outlet. You can see the inferior wall. You can see the mitral valve. You can see the left atrium. Okay, then they have the apical two chamber. The apical two chamber This one, you'll see how you move the cursor when it is at the fourth, fifth, in the mid clavicular line at the fourth and fifth intercostal space. Then this is, you are going to get, this is called to apical chamber. This one you direct the right towards the right, the left shoulder, while the left parasternal long axis is the one which is points towards the makes and towards the right shoulder. This is what you see. In that one, you can see a various structure. You can see inferior vena cava in descending aorta. You can see ascending aorta. You can see aorta outlet. You can see the wall, the inner part of the wall, the mitral. There you can see the aortic outlet. You can see the left ventricle. You can see the right ventricle. Also, you can see the papillary muscles. You can see the mitral valve. You can see the mitral valve, and also you can see the left ventricle there. Okay, you can even see the papillary muscles there. You can see even the papillary muscles there. Okay, so this one you have to compare it with that one, with this one. Okay, so then you check another one, you check the left ventricular short axis. You can be able to check the mitral valve. The left ventricular short axis, you have to check the mitral valve. The mitral valve, you check the papillary muscles. You can check the anterior papillary muscle, the posterior, the left ventricle, the left ventricle, then the right ventricle. You can see that that is how it looks like in an ultrasound. It looks like that one. And then you can see the aortic valve in a short axis. You can see the mitral valve, which looks like the Mercedes sign. Then left ventricle short axis, you can see how the aortic valve looks like. The aortic valves look like short axis. You can see the papillary muscles, all these ones, you can see how they look like. Now, this is the parasternal short axis. The parasternal short axis for mitral valve, in this case, the cursor is put between fourth and fifth intercostal space, mid-clavicular line, and then it is pointed towards the left part of the bed or towards the right shoulder. You'll see these ones as move out. Then you see this one, you'll see the right ventricle, you'll see the right ventricular outlet, outflow. Then you see the mitral valve, anterior and inferior. Then the lateral wall, that is parasternal, you check the mitral valve, then that is how it looks in an ultrasound. Very well shown there. You can see this is the mitral valve, this is the mitral valve, the left ventricular outlet, the left ventricular outlet, and then you can see the right ventricle, the right ventricle. You can see the anterior, the inferior part of it. You can see the lateral wall. This is the lateral wall. You can see the lateral wall, how it is like. And somebody who is experienced can also tell what is this one, and also is the mitral valve is more of ascending aorta. It's more of ascending aorta. This is the descending aorta. Descending aorta. This is the ascending aorta. So, so the various thoracic echocardiogram of views, that is how it is. This is called the apical four-chamber view. The apical four-chamber view. The apical four-chamber view looks like that. The apical four-chamber view. You see that there's the left ventricle. You'll be able to visualize the left ventricle, the right ventricle. This is the intraventricular septum. You can see that because it is dense, it is very bright. Then you can see the intra-atrium septum. You can see this septum. You can see the mitral valve. Then you know this one is longer. This one is longer than this one. Left atrium. You can see the left ventricle. The left ventricle. You can see the heart rate. The heart rate. The aortic outlet at this point. Okay, the left outlet at this point. So you can see the mitral valve, the left atrium. So that is how it looks like in these parts of, you can see the atrium, the intra-atrial, the apical chamber, the tricuspid valve there. Then the subcostal, you can see that is how it looks like. So the subcostal, you can be able to see the right atrium, the interstitial septum, and then the mitral valve, the left ventricle, and also the aortic valve. You will be able to see the tricuspid valve and the left ventricle and the intraventricular septum and the apex of the heart. So in this case, you can see this is the subcostal, and this is the apical fourth chamber. That is the apical fourth chamber. You can see this one is the mitral valve, the intraventricular septum, the left ventricle, which is giving out this. Then you can see the left ventricle. You can see the right ventricle, the intraseptum septum. Okay, the tricuspid valve is here. You can see the right atrium, the apex of the heart, Okay, the apex of the heart. This is the outlet, inferior outlet. This is the inferior aortic outlet, the descending aorta, the descending aorta, the ascending aorta at that. So you can see also this. Then let us see the various echocardiographic views. So there's the parasternal long axis view, which is called Plaque's view. Then we have parasternal short axis view, which is called P-Sachs view. Then you have, in this P-Sachs view, you have basal aortic level, you have middle cavity or mitral level, papillary level, apical level. Then you have apical chamber, apical 2, apical 3, apical 4, and apical 5. So in this case,
so next thing we're going to do is a comparison of long axis view.
So in this case, we see the structure seen on P parasternal or long axis, and this one, you remember that you are putting your cursor at the fourth, fifth intercostal space, mid-clavicular line, and it is pointing towards the right shoulder. That is your cursor where it is now. Okay, so at this point now, you are able to see various structures like the left ventricle, the left ventricle, the left atrium. You see the intraventricular wall, internal wall of the left ventricle. Then you see posterior mitral valve reflect, anterior mitral valve reflect, and you remember that the anterior mitral valve is a little bit longer than the posterior one. Then you can see the left ventricular outlet, and then you can see the right coronary commissus, the non-commissus artery, and then the right commissus coronary artery, then non-commissus coronary, then you have the aorta, then you can see the DOA means the descending aorta, then at this point, left at the far point, you can see the descending aorta, then you can see left ventricular outflow, can see the left ventricular outflow, the left ventricular outflow. Okay, you can see it there. It is the parasternal long parasternal long axis. Okay, in this case, you can see now in motion mode, when you put this one in a mode, you will be able to see the left ventricle, the aortic, the aorta, so that you can see the movement of this one. So you put it along this axis so that you can be able to see this one. This one will be able to measure the longest distance during the systole and the shortest distance during the diastolic piece. Okay, you'll be able to see them how they look like. You can see now it is moving. That is how it is. So something like that. Okay. So in that case, you see that you put your cursor there, then it is telling you, you can see the condyle, tendinite. You remember these ones are the structure which support the valve in position. You can see them. Then you measure the left ventricular and diastolic diameter and right ventricular and systolic diameter. These ones are going, this one you put them at the shortest point, and then this one at the longest point. This is the systolic piece, and this is this one is the diastolic phase. So the intraventricular septum, this is the intraventricular septum, this is the left posterior wall. Then you will be able to, this one will measure now the size of the ventricle. We measure all these ones, left ventricles of volume. We measure the volume on this left ventricle in this case. So you can see on top of it, you have left ventricular outflow, how it looks like in that case. Okay, that is in the mitral valve. So in this case, you put the cursor at the base of the left ventricle, just distal to the mitral valve reflect tips, especially the posterior one. That is the tip of it. That is where you put the cursor, and then you put it in a mode. Put it in a mode. So a mode of aorta, this one from the P long axis view, this is the cursor to the transect of the closer line of the aortic valve. The closer of the aortic valve, and this is the aortic valve. So you put it at the closer of this aortic valve. Then in this case now, you will get this one as a M mode. This one is a M mode. You can see how it is going to play. You can see how it's going to play. And this, in this case, you will be able to get the aortic diameter at the end of diastole and the left aortic diameter at the end of systole. And this is aortic aorta. This is the aorta. This is the left atrium. And the left atrium. This is the aorta. So this is the end diastolic. This is the systolic phase. Okay, this is the diastolic, this is the systolic phase. So you can be able to get these diameters at that point. And you can see the aorta represented here. The aorta represented here. This is where the aorta, the blood is flowing in the aorta, left ventricular outflow, left ventricular outflow, and this is the left atrium. So you can see how these things happen. Okay, so that is how you see those things will happen. So let us see what structures do you see in the short axis of parasternal short axis view. In the parasternal short axis view, what do you see? In this parasternal, first of all, you should understand how should you rotate the probe. The probe still it is at fourth, fifth intercostal space, mid-clavicular line. Now, and it is pointing the right shoulder. Now, there, you twist it slowly, it points the left shoulder. it makes a 90-degree clockwise. Okay, it makes a 90-degree clockwise. From this one, you will be able to see the base of the base of the heart. That is the px axis view. Then you'll be able to see it at that point. And these are the structures you see at this point. You will see that the left atrium, the left commissus coronary artery, non-commissus artery, left, and then the left and right commissus artery, the intercostal intra-atrium septum. You see the left ventricular outlet, the left ventricular outlet. So then you see the TV and the posterior of the ventricle. Okay, posterior wall of the ventricle, and you'll be able to see the posterior mitral valve reflex, the anterior mitral valve reflex, the anterior commissus, and also posterior commissus in these types of X-rays. Remember, so from the M view, from this parasternal short axis, the M view, that is the mode view. The M view is the motion view, the PX view. You see the papillary muscles obtained by angling the sound beam inferiorly until the anterior wall. Inferiorly until you point it inferiorly until it is there, until you get the lateral and posterior medial papillary muscles are seen. So until the muscles and papillary muscles are seen. So you can see the posterior papillary muscle, the posterior anterior papillary muscles in this one, left ventricular outlet, intraventricular septum, left ventricle and left ventricle wall, and that is how it looks like in this type of this one you are checking on this valve. You can see those ones. So you can see the four-apical chamber window. The four-apical chamber window, the transducer is placed on the fourth intercostal space, fifth, and the patient mid-clavicular vein with the image marker towards the left side of the bed. So at this point now, you make the marker outwards. So ensure the sound beam transects through the left ventricle, apex, all chambers are full and valves opening as wide as possible. So at this point now, you move it outwards, and then you'll be able to see these valves. You will be able to see the apical chamber. You see the ventricles, the septum, the intraventricular septum, the atrial septum, the atrium, all of them. You can see how it is moving. You can see that. You can see how it is moving. Let us split it again. You can see how it's making it very comfortable. Good. So then we have the structures seen in this effects is that the transducer is placed and the transducer is placed at the 45th intercostal space, and then the patient mid-clavicular line with the image marker towards the left side of the bed, and ensure the sound beam transect the left ventricle apex, and that is what it is going to give to you. It is going to give you the anterior mitral valve reflex, the posterior mitral valve reflex. Then, and you can see the anterior mitral valve reflex is always longer than the posterior. You can see the anterior, the anterior wall of left ventricle. Anterior left ventricle wall. You can see the left atrium, interatrial septum, left atrium. This you can see the anterior anterior ventricular reflect, the posterior tricuspid valvulets. You can see them there. You can see the both the valves, and also you can see the left ventricular flow, left ventricular, and so those ones you can see the apex. Remember that in ultrasound, it is a mirror sized. The reason why you see that the heart is upwards, downwards. The apex in a normal person is on the lower side, but in an ultrasound, it is on the top. That principle, we should always remember it. So the Doppler ultrasound studies gives so many views like those ones. Okay, gives so many views like those ones. So you can see that one. You can see this one is when you are checking the velocities. When you are checking the velocities, you have to check the structures and the velocities. Okay, you want to measure the velocities. Okay, the tricuspid regurgitations. Now, you should remember that if you want to measure the regurgitations, you use the Caramond. The Caramond where you check the blue and red. Okay, and remember that the blue and red, and the principle is that the blood which is moving away is blue, the one is moving downwards is reddish, once is reddish, that one is very important. So in that case, you get you put the cursor there in that valve, you across the along the valves, cuspid valve, you get that one. Then you measure that, bring that measurement there. Okay, so the basic principles of Doppler is that the Doppler effect was discovered by us. Okay, was discovered by Austrian physician called Christian Doppler in that time, and it's the one which is used to just as ground flow. So you trace the measure. So in this case, you measure the difference. You can see that the blue is moving when the blood is moving away, and then is the blood is moving towards. This one is when you get the velocities. So the Doppler mode is you have the current Doppler, the power Doppler, and the past wave Doppler, and the continuous wave Doppler, and the spectral and Doppler. So the current Doppler is in imaging is the Doppler information is superimposed within the simple box shown on the Beaumont images. Image and colors are used to represent the direction and the speed of blood flow. For example, the red may indicate blood flowing towards the transducer, while the blue may indicate the blood flowing away from the transducer. Okay, the blue towards the blue is away from the transducer, and then the red is towards the transducer. That is the principle of regurgitations. So this mode ignores the direction of information provided by Doppler and received and displays the total Doppler signal towards the center of our color. Which it does not display any data on flow direction. Power Doppler is a useful tool for examining low velocity blood flow and is more sensitive to flow than the color and Doppler. So the continuous wave Doppler uses a continuous ultrasound beam to continuously sample blood flowing along a specific line. So continuous wave Doppler is particularly useful for obtaining high velocity blood flow information like flow across the aortic valve or flow across regurgitations. So a pulse wave Doppler sends short pulses of ultrasound and receives the reflection allowing for precise localization of the blood flow. So it allows for more accurate localization of blood flow, making it suitable for standard and specific valve areas. So as the spectrum and Doppler is provide a Doppler data in a geographical representation of blood flow velocities over time. Velocities is plotted on y-axis and time is plotted on x-axis. So flow towards the transducer is plotted above the baseline and flow away from the transducer is plotted below the baseline. Both the continuous wave and pulsed wave Doppler system can be displayed in a spectral format. So this is the continuous wave Doppler of aortic valve flow. That is how the aortic Doppler flows. The power wave Doppler of a mitral valve, that is how it looks like. And then you can display flow everywhere in the heart spectral Doppler are several uses assigned from those mentioned above. It can display sound flow of a ventricular septum defect or in the atrial septum defect. To find the jet, also it is good to use current Doppler first. To use the calendar for that. So basically, that is a very informative topic. We have studied today about the basics about the ultrasound. We have studied the most important thing is that we have studied about the transducers, various types of transducers. We have seen the cardiovascular types of transducer. We have seen the various scanning modules in displays. We have seen the parasternal, the short axis, and the long axis. We have seen the apical view. We have seen the basic principles of Doppler. We have seen the ultrasound imaging of the and the artifacts and the principles of imaging. Thank you very much for listening to this informative lecture, and we'll continue interacting so that we can be able to discuss more. Thank you very much.